Hi everyone. In this chapter we will be looking at rational expressions. In this lesson we will be looking specifically at simplifying rational expressions. To begin, we'll start by looking at some definitions.
Alright, so now we're starting to talk about rational expressions here, and we're going to start off with just by simplifying rational expressions, and we're going to talk about non-permissible values. It's kind of a really big idea in this particular chapter here. Now we'll start with a definition. So it says right here, a rational function is any function which can be written in the form f of x is equal to n of x over d of x. Okay, so notice we got two functions here, numerator and denominator. That's why we've chosen n and d, where d of x can't go to 0. Okay, that's a key point, one that we're going to come back to actually repeatedly throughout this chapter. Okay, so n and d are both polynomials. Now we've got this other little comment right here, d must be degree 1 or higher. Now what that's saying essentially is that, at least in this context here, what they're saying here is that d of x can't be a constant. Now, just to be clear, it's not because it's not a rational at that point. It's a rational. It's still a rational number here, or fraction here, function I should say. It's just that if the denominator is degree 1, if the denominator is degree 0, if it's a constant, this is better called a polynomial as opposed to a rational. This just becomes the definition of it at that point. It's still rational. In fact, rational is kind of an overarching name that we give to a group of these objects here. Specifically, a polynomial is a rational where the denominator is a constant. Okay. So anyway, so here are some examples. We've got here. We'll zoom in a little bit here. Okay. We've got x plus 2 over x minus 1. Okay, polynomial. It can be 1 over x squared minus 9. We have no problem with the numerator becoming 1. 1 over x can be as simple as that if we want. But now down here, we've got x plus 3 over 5. Now this is still rational. Okay, this is still rational. I need you to know that. Okay. However, there's going to be some insistence here that it's not rational because we want to push you towards a different definition here. Call it, in fact, it's probably better not to say it like this. It is rational. Okay, it is rational, but call it polynomial. Okay, give it this name right here. Now, the next thing that we want to look at when we talk about these rational functions here is the non-permissible values. Now, we had mentioned up here, way up here in the definition, that d of x can't be equal to 0. Now, go to your calculator here. In fact, let me show you here. Let's take and we'll divide something by 0 here. Let's say 9 divided by 0. Notice we get an error. Okay, can't divide by 0. That is undefined. So there is a problem whenever the denominator goes to 0. Now, in a rational function, you're going to have a little polynomial down there. It's going to have a little x in it and whatnot. So what we can't allow is we can't allow that function, the x in that function, to take on the specific value that makes the denominator go to 0, because that leads to an undefined. That's what we call a non-permissible. Okay. Now it's very common for people to immediately assume, because we know that 0 is the problem, to immediately assume that 0 is the non-permissible value. Okay. Let me write it down here. 0 is not necessarily, okay, a non-permissible value. It can be, but it's got to be a very specific situation here. That's not a true statement for all of them that 0 is a non-permissible. And in fact, let's take just a quick look here. So notice we've got this rational function x plus 3 over x minus 5. It's the x minus 5 that is the concern here because it's the denominator. X minus 5, we cannot allow that to go to 0. And having an equation like this with a not equal in it, you treat it just the same as you would as if it was an equal sign. So you're just going to add the 5 to both sides here. And so right away we determine that x can't equal 5. If x is 5, I get a 0 in the denominator, and that's undefined. But that's the only one. 0 is not a problem. In fact, if I plugged 0 into x here, I would get 3 over negative 5. Nothing wrong with that number. 3 over negative 5 is fine. It's good. But putting a 0 down there is no good. Anyway, let's take a look at some examples.
Determine the non-permissible values of the following.
Okay, now let's figure out the NPVs of a bunch of rationals here. So first of all, 3 over x minus 2. Well, again, it's the denominator that we can't allow to go to 2. Sorry, I did that a little quick. Sorry, I should have written it like this to start off with. Jumped on that a little quick. Should be x minus 2. Can't allow that to equal 0. And then I'm going to bring the 2 over. X cannot equal 2. Now, here's a situation right here where x is all by itself in the denominator here. Here's a place where we can freely say that x can't be equal to 0. That's the non-permissible. Over here, x could equal 0. If x is 0, 0 minus 2 is negative 2. 3 over negative 2 is fine. It's just negative 3 halves. That's not a problem here. Here, I don't even care about that 7 plus x right now. All I know is that x plus 2 can't equal 0. Now notice these are multiplied together, okay? So if x plus 2 equals 0, when I multiply them together, the whole thing equals 0. On the other hand, if x minus 1 becomes 0, and again, when you multiply those together, the whole denominator becomes 0. So I'm going to have two non-permissibles here. In this case, x can't equal negative 2 when I solve for x. And at the same time, x is not allowed to equal positive 1. So there are two non-permissible values for this problem. Here, again, there's just the one term in the denominator. It's a little different than the previous ones, though. We've got one more step here. Just look at it like this. 2x minus 3 can't go to 0, which means 2x can't equal 3. But now I've got another step here. I can't allow x to equal 3 over 2. I'm going to divide both sides by the 2 to get that final result, final non-permissible. Okay, now here. This is the one that's going to cause a little bit of confusion here. There's a couple little issues here. First of all, notice that I've got 2 times x times 6 minus x here. Now, I mean, I could jump up and say, hey, this factor right here, 2, can't equal 0, but 2 doesn't equal 0, so please don't even try that. That's ridiculous. But this x here, x could be 0. And when it shows up all by itself as a factor in the denominator, then there's a restriction that goes with it. I can't allow that x to be to 0. Now, if I allow one x to be 0, they all go to 0. But this one will cause the whole thing to become 0. And then it's this factor right here, because there's an x in it, I can't allow that factor to go to 0 either. Now, when I bring that x over, we're going to get here our two restrictions here. X can't equal 0 and x can't equal 6. Here, now there's a couple of ways that you might go about doing this, really. But essentially, it's going to boil down to this. The denominator, x squared minus 16, cannot be equal to 0. Now, there's a couple ways you can do this. Maybe what you might do is bring the 16 over, and you'll get x squared cannot equal 16. But now, when you go to the next step here, remember, I'm going to take the square root of both sides, but because this was x squared, I don't know whether that x was supposed to be positive or negative. Either way, squaring it would have gotten rid of that negative, made it positive here. So the square root of 16 is 4, but it could be positive or negative 4. There are two non-permissibles here. Essentially, anytime you've got a square there, if you think that back to Math 20, you're going to get two roots. Okay? Now, they may be the same number, or they may be two non-real roots, but you're going to get two roots typically. So, and then again here, last one, okay, I've got x as a factor all on its own here, so I can't allow that x to go to 0, which would mean all of the x's, but in particular, this one's going to cause the problem. And then here's this factor right here. It's got an x in it, so I can't allow 3 minus x to go to 0. And so there you go. X can't equal 0, x can't equal 3. So those are our non-permissibles. Now, whoops, I'm just going to take a look here. There are a couple more questions here from this lesson. All right, a couple more here. Factor in the denominator, factor in the denominator. Okay, so 3x minus 1 as one factor here can't go to 0, because if it does, the whole thing goes to 0, just like 2 minus x can't go to 0. So let's bring over the 1. 3x cannot equal 1, and then divide by 3. So my first non-permissible here is 1/3. Can't have it go to 1/3. Oopsie daisy, sorry about that, everybody. And then the next thing I'm going to do is bring the 2 over, and I get that x can't equal 2. Okay. Now this one's a little bit different. Okay, this one's a little bit different. 3x squared plus 4x, I can't allow that to go to 0. Now, what I can do here first, though, is factor out that common x. So 3x times 3x plus 4 I can't allow that to go to 0. And then I can take it and split it into those two pieces. So what I had to do here, first of all, was factor that. And then I'm going to get that x can't go to 0. That's this little factor all on its own. And now 3x plus 4 can't go to 0. Okay? And so 3x cannot equal negative 4, and then x can't equal, I don't even know if that's still on the screen there. There it is. X cannot equal negative 4/3. Now, someone might look at this problem and say, well, wait a minute. Is it really can't equal 0? Because can't I cancel out those x's there? Because there's a common x to all those terms. And yeah, you can cancel that to simplify it. Okay? But, okay, when you do that, you're going to get an expression here that's only approximately equal or equivalent to, is maybe a better word, to 3x plus 4. Yeah, there's a common x there, and there, so you can cancel them all out here. But that's not exactly equal to this expression, because this expression is undefined when x is equal to 0. If you plug 0 into this right now without doing anything, it's undefined there. If you plug 0 into this, it's not undefined. So these are not exactly the same. Okay? And in fact, the only way to make them the same would be to say, if you were to throw in this little comment here that x can't equal 0. And then I make that equal, because the one spot where these two aren't the same is when x is equal to 0. That's where this thing is undefined. So if I just include this little statement here that x can't equal 0, then they are the same. So either way, even if you try to cancel that x out, you still get stuck with this non-permissible x can't equal 0. So honestly, the best advice I can give you is don't worry about the numerator when you're trying to figure out non-permissibles. Okay, don't worry about it at all. And then finally, this question right here, I've got x times y squared. So x is a factor all unto itself, so x can't equal 0. And y squared is also a factor unto itself here, so there we go. And then when I take the square root of 0, well, the square root of 0 is 0. It's not even plus or minus 0, because that really doesn't make any sense. It's just 0. So x can't equal 0, y can't equal 0. Those are your non-permissibles.
Now we'll look at the process of simplifying rational expressions.
All right. So now we're going to talk about simplifying rational expressions, and I've already kind of given you a hint as to how to do that. But here we go. Here are the steps. First of all, we're going to factor the numerator and denominator. We're going to identify the non-permissibles, and then we're going to simplify if possible. Now, by simplifying here, essentially what we're doing is we're identifying that if you've got a divided by a, the response is 1. Okay, the result is 1. And remember that 1 multiplied by anything doesn't change it, okay? Whatever you multiply by 1, it maintains its identity. And in fact, that's why we call this the multiplicative identity. It doesn't change anything here. That is the essence of simplifying. I'm going to find a ratio that becomes 1, and then I know that 1 times whatever's left over is just going to stay like that. The mistake that so many people make is a divided by a is 0, right? They cancel. No, a divided by a is 1. Now let's take a quick look here. And there's a little bit of an add-on that I have to make here. Okay, so the following expressions here are equivalent. Okay, the following expressions are equivalent. Now we're going to work this thing through here. There's something missing here. I'm going to show you what it is in a second here. 3xy over 5xy, z here. Now, we canceled the x over the x. Now, when you do that, really what's going on here, you shouldn't use an equal symbol there. You should use the equivalent symbol. These are not the same. Okay? They're not the same expression. They are really close to being the same, but they're not the same expression because of the x here. There is a restriction here that x can't equal 0. Okay, right here. If x equals 0, this becomes 0 over 0, and that's undefined. Over here, there is no x, so there's no issue that way. So they're not the same function here. So the only way I can make them the same is by including in this that little non-permissible that x cannot equal 0. Once I do that, now they're equal. Okay? This automatically has the restriction that x can't equal 0. Here I need to state it because it's no longer visible. Now there is another non-permissible here that z can't equal 0, but I'm stuck with that one. I can't get rid of it. It's in the denominator. Okay? So, which is why we give these a couple of different words here. This this little non-permissible, if you want to really give it the right name here, is called a removable discontinuity. I mean, don't worry about what I'm getting at there, but that's what it's called. And then when z can't equal 0, that's called, oh my gosh, I just lost it. It was it's not a necessary discontinuity. It's a, oh my gosh, I forgot. I had it like 2 seconds ago. It'll come back to me. This is called removable, and then there's a name for this one when you can't get rid of it. Ugh, that's embarrassing. Let's move on. Okay, here we go. So 2 more expressions that are, these are not the same quite yet. They are equivalent though. Okay, because notice that this thing right here is undefined when a is equal to 0 and when b is equal to 0. But here, this expression isn't undefined anywhere. They're not the same function. They're very, very close to the same function, but they're not the same. In order to make them equal, I would have to state here that a can't equal 0, and at the same time b can't equal 0. Then I have reintroduced, okay, the non-permissibles that existed on the left-hand side. Okay, I simplified by getting rid of them, but I need to state that in order to make this equal. Because if I don't, if I drop that, they're not exactly equal. They're only what we would call equivalent, which essentially means that there's a set of points where they don't actually match up. They're close, but not perfect. Here, same sort of thing. So I've got this expression right here. Notice I've got this x minus 2 over an x minus 2. Okay, I was able to cancel. That becomes a 1. And when you multiply that 1 by what's left over, you get to keep it. These are not equal. They are equivalent. Okay, until I state the missing non-permissible here. And in this case, if x minus 2 is one of the factors, then the non-permissible here is that x cannot equal positive 2. Once I do that, those become equal because now I've put that non-permissible back in. Now I could state that y can't equal 0 and that x can't equal -5, but I can see that those are already there. This is the one that's no longer visible because I canceled. I need to include this one by writing it out because I canceled it out here. It doesn't exist normally anymore. Okay, so that again, there's my removable discontinuity. These two are the, I was hoping the word was going to come back to me right there. It's not a necessary discontinuity, but it's kind of that word, that kind of idea. You can't get rid of it. All right, so looking down here, whoops, where are we going here? We're going to simplify and list the NPVs here. So look at our numerator denominator here. First of all, we're going to look for common factors. So we can factor 48 a little bit, and we can split up the xy squared and the xy squared. So we get this. 16s will cancel. The x will cancel. The y will cancel. Now, notice that when we do this, okay, the x is canceled, yes, but I was still left with another x in here. So I can see right away that x is still a non-permissible. What I've lost here in the simplifying is that, you know what, because there was a y in the denominator originally, there was another non-permissible here that y can't equal 0. Now, before I write that, these are only equivalent. They're not exactly equal, they're only equivalent. You state that non-permissible in there, now they're equal together with that. Now, when we talk about the non-permissibles, you're going to say that x can't equal 0 and y can't equal 0. Now, I'm going to come back to this. You don't absolutely need to state that x is non-permissible here because I can see it. It didn't go away, it stayed there. However, this is high school, and we need to know that you recognize what the non-permissibles are, so we're going to encourage you to state them all. Okay? So now that's something that I haven't done up to this point here. I've been only focusing on the one that was absolutely necessary because I want to give you a sense of like what is necessary, what isn't, and the idea, the difference between equivalent and equal. Okay. This is all I needed to write to make these two expressions equal. This one here is really just so that you get the mark. You got to do what you got to do, right? All right, so just before we go on and do some examples, just some more warnings here. Please don't do this. When you've got x plus 3 divided by 3, you can't just cancel those out. Okay? You could if it was x times 3 over 3. Okay, and that's because multiplication and division can kind of happen in whatever order you'd like. So I can divide the 3's and then multiply by 1 here, but here I can't. And the reason I can't is because when you've got a binomial in the numerator, denominator, or even a polynomial, there's always an implied set of brackets there. So you have to do the addition first. You have to do x plus 3 before you can divide by 3. And if you don't know what x plus 3 is, then you're done. That is as simple as it could get, x plus 3 over 3. Same thing over here. There's an implied set of brackets here, which means I would have to add x plus 5 before I could divide by x. And because I don't know what x is, I don't know how to add them, that's a dead end. That's as far as I could go. And then the same sort of thing here, right? This time there's an implied set of brackets around the numerator and the denominator. Can't cancel those x's because I can't complete the operation up here. So that is as simple as that would get. So just be aware of your order of operations and be aware that if you've got a polynomial in the numerator denominator, there's a set of brackets implied by that line. If you just keep thinking about it like that and stick to your order of operations, you should be fine. A couple other things to worry about here or to think about. If you've got x minus 3 over 3 minus x, notice the signs are what's different here. So what you can do in the denominator here, for example, is simply factor out that negative. And then the x minus 3 over x minus 3 is 1, but there's a negative in front. So really, if you want to think of it a little bit quicker there, that makes that negative 1. Now, in this case right here, the signs are exactly the same, numerator and denominator. The order's changed. Remember, order doesn't matter for addition or multiplication. It's because addition, okay, is commutative. Now, if you don't remember what that word means, I know you've seen that before, but if you don't remember what it means order doesn't matter. Okay? Not everything in math is commutative, but addition and multiplication specifically are. So you can flip that around. They're both equal. This would just cancel and be equal to 1. All right, now let's look at some examples.
Write an equivalent expression and list the non-permissible values.
Right, so we're going to simplify these expressions and then list the NPVs here. So now I'm going to use this symbol right now. I'm going to get rid of that in a bit. You're going to use this symbol right now. So 18 and 3 have a common factor of 3. And in fact, this is 6 times 3. So when I cancel 3 here, we'll be left with 6 in the numerator. And then x to the 6th divided by x cubed. Well, I've got 6 of them in the numerator, 3 of them in the denominator. So a group of 3, numerator and denominator, will cancel. I'm going to be left with x cubed. Now, these are equivalent. But as soon as I state that x cannot be equal to 0, they become equal. Okay? Because now I've included that non-permissible that was missing here. So that was present here, but is now missing here, I should say. Here, I use the equivalent symbol. Well, negative 22 divided by 11, that's easy. It's negative 2. A cubed divided by a cubed, well, that's wonderful. That's going to be 1. B squared divided by b is just going to be a b here. So this expression right here is equivalent to this one. They don't become equal until I state, notice that a can't equal 0. Okay, it's its own factor in the denominator. B can't equal 0 for the same reason. And as soon as I state those two, the right-hand side is now equal to the left-hand side. Here, once again, we'll do the equivalent symbol here. Now 15 and 8, they have no common factors. They're what you would call relatively prime. They're not prime on their own, but when you compare them, they got nothing in common, so that's why we call it relatively prime here. So I'm still going to have 15 over 8. That's not going to change. I've got 4 factors of m in the numerator, 1 in the denominator, so canceling 1 out will leave me 3 up here. I've got 6 factors of n in the numerator, 7 in the denominator, so all but 1 of them will cancel, and that 1 will be left in the denominator. Now, these are just equivalent until I state that m cannot equal 0. Now, m is its own factor down here, but look at over here, it's not in the denominator. Here, it's missing. So now by stating that, they're going to be equal. Now you might look and say, but wait a minute, you've forgotten to include the n can't equal 0. And yeah, but that non-permissible exists here as well. that n can't be 0 here is true, n can't be 0 here is true. But here, m can't be 0 because it's in the denominator, and here it's not in the denominator anymore. So unless I state that m can't equal 0, I would never know by looking at this, but I already know that n can't equal 0. However, you'd be right if you assumed, yeah, but don't I have to do that to get the mark? Yeah, that's exactly right. So you do need to include that. It's just that mathematically speaking, it's not necessary to state that to create equivalence between those two. A few more examples here. Okay, 3x 4 minus x over x minus 4. Okay, these are going to be equivalent. Now, the 3 and the 12, well, there's going to be a common 4 in the, or a 4 in the denominator, because 12 is going to be 4 times 3. There's that x right there. Now, there's nothing to cancel with that x, so it's actually nothing's going to happen to it. Now, 4 minus x over x minus 4, notice that these are exactly the same binomials, but the signs are different. So think back to what we discussed before. That's going to mean that when these cancel, I'm just going to get a negative here. Okay, instead of becoming a 1, they will become negative 1. Now, these are not equal. They're equivalent. What value of x would cause this to be undefined? Well, it's going to be 4. X cannot equal 4. And once I make that statement, those two terms are equal. Okay, now I hope you get what I'm saying here. Like, it's the whole right-hand side, this including this, that I need together to be equal to what's on the left. This one right here, again, I'm going to start with my equivalent signs here. Actually, this is beautiful. Oh, I love this one here. 6 divided by 6 is 0. A squared, I cannot believe I said that. Oh, I wish I could just turn it back. I told you before it wasn't 0. 6 divided by 6 is 1. Is 1. A squared divided by a squared, 1. 2a plus 5 and 5 plus 2a, these are the exact same term polynomials there. Order doesn't matter with addition, so they all become 1. However, I need to state the non-permissibles to make these equal. A can't equal 0. I get that from this a squared. And then right here, 5 plus 2a can't equal 0. Well, bring that 5 over. So 2a can't equal negative 5. A can't equal negative 5 halves. And once you've stated that, now I can write that they're equal to each other. Okay, now finally, something that we're going to have to play a little bit with here. I'm going to have to factor a little bit here. So I can take out a common a here, and that'll be 2b minus c. And I can take out a common 3 here, and that'll be 2b minus c. Now these are equal because I haven't canceled anything. I've just written them differently. Okay, so these are equal. However, this will be equivalent to, I can cancel the 2b minus c. This will be equivalent to a over 3. Not exactly the same, but equivalent. As soon as I state what the restriction is, and the restriction is over here that 2b minus c can't equal 0. Bring the c over. And I mean, you could leave it like this if you wanted. I suspect most of us would probably do that. B can't equal c over 2. Okay, b can't equal c over 2, and as soon as I do that, I can use the equal sign. There you go.
And now we'll spend some time looking at more complicated rational expressions.
All right, now let's talk about the process of simplifying these complex rational expressions here. Now, we've already kind of seen this. This is now just kind of formalizing the procedure that we've been establishing here. So what we're going to do here is, first of all, we're going to factor. Okay, numerator and denominator. Okay, numerator and denominator. We're going to state the non-permissible values. Okay, and then we're going to reduce. We're going to find those ones. Okay, where the factor in the numerator divided by the factor in the denominator. So as an example right here, just to introduce this here, so what we would do is something like this, is we would look at the numerator. I see a difference of squares. So x plus 3, x minus 3. And then I see a trinomial, which would require some basic trinomial factoring. Now we're looking at factors of negative 6, whose sum is negative 1. And that's going to be negative 3 and positive 2. Now, notice that my non-permissible values at this point here would be that x cannot equal, now look in the denominator, can't equal positive 3, can't equal negative 2. And now x minus 3 divided by x minus 3 is going to go to 1. Now, when those factors are gone, that's 1 times x plus 3 divided by x plus 2. So this reduces down to x plus 3 over x plus 2. However, I need to keep stating the non-permissibles. Mostly because, as we've seen before, mostly because as soon as I've canceled out here that x minus 3, that non-permissible is gone, right? Down here, this no longer has a problem at 3. So what I need to do is I need to include that, like to state, hey, by the way, remember, that was a problem here in order for these to be equal. Because until you write that, remember, these are just equivalent. Okay, they're just equivalent. These are not exactly the same until you state the non-permissibles, in which case they become equal. This one, you absolutely need to write. That one, yeah, you don't absolutely need to write it, mathematically speaking, but you do need to write that to get the mark.
Write an equivalent expression and list the non-permissible values.
So now our goal in this set of example questions here is going to be to find an equivalent expression here. So here we go. To start off with, we're going to state what this is equal to by factoring. Now in the numerator, I see that there's a common factor of 5. That's going to leave me with 5r squared plus 2 divided by 25r squared. Now the non-permissible here is going to be that r, I can't let r go to 0, because if r goes to 0, then the denominator goes to 0, and so on and so forth. There's really not much that I can do to simplify this other than the fact that 5 and 25 both share a common factor. Now, remember, what I got to do here is I can only cancel factors, and my factor in the numerator is 5. The factor here is 5r squared plus 2. So there are 2 factors in the numerator. Now there are a few factors in the denominator because 25 consists of 5 times 5, and then I've got this r squared here. But the only one that's kind of shared between them is that single 5. And so that'll become 5r squared plus 2 over 5r squared. I don't absolutely need to say that r can't equal 0, but if I want to get the mark, I really should. Now, the temptation here with a question like this is to want to cancel that 5r squared there, but you can't. Because remember, that line implies a set of brackets around the numerator and the denominator. And so I would have to do what's inside the brackets first, and I can't add those two together. So because I can't add those two together, I can't move on and do the division. I cannot cancel those out. Even if you tried to do this, you'd have to distribute that to both those terms. The mistake that most people make is when they try to divide this, they only divide it through one term, and that's incorrect. You would need to either do it to both or none. Okay, so keep remembering that. Let's look at the next one. All right, so in this case here, again, we're going to yank out what's common, and to the 18 and the 30, that's going to be 6, and there's an x in both of those terms. The smallest exponent is squared. When I pull it out, I'm left with 3x minus 5. Down in my denominator, I've got 24x squared. My non-permissible will be that x can't equal 0. Now bear in mind, that is not always the case. 0 is not always a non-permissible, but in this case, because x is a factor in the denominator all on its own, okay, it is. It is a non-permissible. Now, the 6 and the 24, there's a common factor there, and then more importantly, the x squareds are going to become a 1 here. So here, basically, I can divide that whole factor away, and so I'm going to be left with 3x minus 5 in the numerator. Now in my denominator, the only factor that's going to survive here is the 4 out of the 24. And again, this time I absolutely need to write that x cannot equal 0 because that doesn't exist as a restriction here in my answer. It does in this problem though, so I have to write it because in order for these to be equal, the restrictions have to also be equal. Okay, this one right here, okay, this one's finally going to have a little bit more factoring involved here. Okay, good. So the numerator is going to be a difference of squares, x minus 5, x plus 5. The denominator's got a common 3 to it. Take that out and I get x minus 5. So my non-permissible will be here that x can't equal 5, because that'll cause this to go to 0. And now, actually, and I'm going to do it like this. I'm really going to stick to my guns on this one. This is going to be equivalent to an expression where I cancel those out and I'll be left with x plus 5 over 3. Those are equivalent because remember this one has a non-permissible at 5. This one doesn't have any non-permissibles. So for me to make these equal, I actually have to state here that x can't equal 5 and then, now they're equal. And that's a reduced expression. Okay, m squared minus 9. Okay, oops, sorry, let me tighten my pencil there. That's a difference of squares again, m minus 3, m plus 3. And now look at the denominator here, m plus 3 squared. I'm just going to write that out. M plus 3, m plus 3, because I got two factors there. And then the restriction here, the non-permissibles, m can't equal negative 3. Now, I've got m plus 3 over m plus 3. Those are going to cancel. And remember, now, actually, I was going to put equivalent here, but actually, in this case, they are equal. M minus 3 over m plus 3. They are equal, and the reason I say that is because the non-permissible up here is that m can't equal negative 3. Okay, that's just the natural result of that factor in the denominator, but I still have it in the denominator because there was two of them there, so that is still here. This still has a non-permissible at negative 3. I don't really need to state that because I can still see it here. In those other questions, that non-permissible disappeared, which is why I had to state it. But here, if I want to get the mark, remember that you gotta jump through that little hoop there. You gotta state the non-permissible. So this is what we're asking for. All right. In the numerator here, I've got a common x squared, and that's going to leave me with x minus 1. Down here, I've got a common x squared, and that'll leave me with x plus 1. Now, my non-permissibles here are that x cannot equal, well, when x squared, whatever, shows up all by its lonesome here, that implies the 0 here. And right here, that means x can't equal negative 1. This will be equivalent to, remember, the x squared divided by x squared will cancel. That'll be equivalent to x minus 1, x plus 1. But these are not equal until I state the non-permissible that I got rid of specifically. And the one that I got rid of is x cannot equal 0. Now I can state that they're equal. Now, I hope you're getting sick of me doing that. I really do. Because if you're getting sick of me doing it, that means you're starting to anticipate that as a result, and you'll start to do it on your own. Okay? Because I'm going to just keep doing it here. But again, I have to state x can't equal negative 1. Even though I can see it right here, I need to state it because I want to get that mark there. X squared minus 36. Okay. X minus 6, x plus 6, because that's the difference of squares. Now, the way I teach this with my students when I go over this, look at the denominator. Now, you've been going to school for years, you've been doing math for years. Something about the way that looks should strike you as odd. It doesn't look right, okay? It looks wrong here. It should be flipped, okay? It should be flipped around here. This should be, and think of this as an addition. Don't think of this as 6 minus x. Think of this as 6 plus negative x, because then I can switch the order. Because with addition, you can switch the order here. With subtraction, you can't just swap things. 2 minus 3 is not the same as 3 minus 2. But if I keep that negative with that term, yeah, I can move it around here. And I get it to look like this. That looks better. It still doesn't look great to me because I don't like having a negative in front of that leading term here. What I'm trying to do here is I'm trying to make it look pretty. And that is honestly the way I teach that. Okay, I talk about math. Math should look pretty. As soon as it doesn't look pretty, it's probably because something is weird about that problem here. So now what I'm going to do is I'm going to take that negative out, and now I'm left with x minus 6. When you factor out the negative, it changes the signs there. That looks pretty. That looks right. I like that. Okay? Now, the whole time here I should have been stating the non-permissibles, but my first goal was to make it look pretty. My non-permissible here is that x can't equal 6, because that'll make that equal to 0. Now, x minus 6 are going to cancel. This is going to be equivalent to, now remember that x minus 6 divided by x minus 6 is going to be 1. But there's this leftover negative here. It's going to be negative 1. So altogether this will be negative x plus 6. They're not equal to each other. They're equivalent until I state this. X can't equal 6. And now I've fixed my problem, and there you go. this expression here is equal to negative x plus 6, so long as x doesn't equal 6? That was a good question. Really like that one. All right, here we go. In this one, a lot of the work has been done for us. Okay, it's already been factored, so actually what I'll do here is I'll do this underneath here. But I will state here that m can't equal, well, m by itself is a factor. Now it's to the fourth, but that doesn't really change anything. M still can't equal 0, and m can also not equal 2. Now here, got some nice things happening. The m minus 2 will cancel, and actually, you know what? They're not equal. They're equivalent until I fix it. The m minus 2's will cancel. I've got m to the 7 over m to the 4. Okay, well that means I've got 3 additional factors of m in the numerator. Everything else will cancel. And then 14 and 21, well they've both got a common factor of 7. When you divide that out, I'm going to be left with a 2 in the numerator and a 3 in the denominator. And so there we go, we've simplified it. Now, however, these are not equal until I state that m cannot equal. Now in this case, both of my factors with m in it disappeared in the denominator, so I need to actually include both of those before I can change this equivalent sign to an equal sign. Okay. Here, oh look at this! I've got another little bout of ugly happening here. I got to fix that. Now, first of all, I notice in the numerator this is a difference of squares. That'll be 5x minus 1, 5x plus 1. All over. Okay, now I'm gonna focus on making that thing look pretty first. This looks to me like adding negative 10x. So now I can change the order. And I'm still not thrilled with that, so I'm gonna 5x minus 1 in the numerator, 5x plus 1. I'm gonna take out a negative, and in fact I'm going to take out the negative 2. I don't want this first term to be negative, and there's a common 2 there, so I'll take out that negative 2, and that's going to leave me with 5x minus 1. Not only is that much prettier, but all of a sudden I can see the common factor. Way better. The non-permissible here is x cannot equal, well now just think about that, 5x minus 1. You're going to bring the 1 over, divide by 5, x can't equal 1/5. Those are going to cancel. And this is going to be equivalent to 5x plus 1 over negative 2. I make it equal as long as I include that x can't equal 1/5. And now they're equivalent here. Now, you might also want to do this, though. Move that negative up. Either move it to in front of the whole thing or move it up to the numerator, but I'm just going to put it in front of the whole thing here, where x can't equal 1/5. That just might be a little bit easier to see what's going on. Putting the negative in the denominator like that, it honestly just looks a little weird. All right, and then finally in this little section here, we got a lot going on here. Okie dokie. Between 7 and 35, well there's a common 7, and then we've got a common x squared. So what's that going to leave us? It's going to leave us with x squared minus 5. Down here between the 14 and the 21, okay, we got another common 7. And then I've got a common x cubed there. So it's going to leave me with 2 plus 3x. Okay, now, state the non-permissibles. Okay, well, x, because x shows up as its own factor there, x can't equal 0. And then in addition, now this doesn't quite look right. Something about that looks a little bit wrong here, so I'm gonna rewrite this. This will be 7x squared, x squared minus 5. Now this kind of looks like a difference of squares, but 5 isn't a perfect square. I'm gonna come here and I'm gonna change the order here. Order doesn't matter with addition, so I'm gonna change the order. That becomes 3x plus 2. Okay, that's way better. That's way better. Now I can come back up here and I know what's gonna go on here. I'm gonna make that, I'm gonna take the 2 over to the other side, so it'll be negative 2 divided by 3. So x can't equal negative 2/3. I'm going to carry that down because that non-permissible stays. This is going to be equivalent. I'm going to cancel the x, the 7's here, and most of the factors of x, but not all of them. There was one extra factor of x in the denominator. Now, I put an equivalent symbol here, but actually I don't need it. They are, in fact, equal. Okay? Because the non-permissibles here were 0 and negative 2/3. Well, here, I can't cancel out any more x's. I can't cancel that x with the x squared because remember, this isn't just x squared multiplied through. This is x squared minus 5. I'd have to subtract that 5 before I could do that division. Well, I can't do that. So this is as far as I can go. So here, there's a 0 non-permissible here. There's a negative 2/3 non-permissible here. It's the same non-permissibles. So those are, in fact, equal. However, if I want to get the mark, I need to jump through that hoop and I need to state the non-permissibles. Okay, there's a lot of examples there. I hope you're starting to get your head wrapped around how we want you to approach these things.
Determine if the following expressions are equivalent.
Okay, now we just got a handful more examples to look at, but it just gives us some opportunity to talk about a couple things. I like this question here. It says, are the following expressions equivalent? Notice what it's not asking. It's not asking, are they equal? I'm not asking, are these two exactly the same? I'm asking, are they mostly the same? Okay, except for maybe a few small things here. So watch this. To figure that out here, what I would have to do is simplify and just see if they simplify to the same thing. Now, 5 over 2x minus 1, there's no factoring to be done here. There's no canceling. That is as simple as that's going to get. But up here, you can play with this a little bit. Can't do much with the negative 15. But notice my denominator it's not pretty. It's not pretty. The x is at the end. There's a negative in front. So I'm going to treat this as plus a negative 6x so that I can change the order, because order doesn't matter with addition. So negative 6x plus 3. And then what I'm going to do here is I'm going to factor the denominator. So I've got a negative 15 up here. Now, remember, this is all equal. Everything I'm doing right now is equal because all I'm doing is moving things around. I haven't canceled anything yet. I haven't changed the function. I'm just altering where things are located. There's a common 3 to both of these, but I want to take out the negative because I don't like it when it starts with a negative. So I'm going to take out a 3, and that's a negative 3, I should say, and that's going to leave me with 2x minus 1 here. Now, I like the fact that there's a 2x minus 1 there. Now, the negative 15 divided by negative 3 is going to be positive 5. This is 2x minus 1. All right. Now, these have been equal the whole way down. I haven't done anything to change it, and it's exactly the same as this. Not only are these two equivalent, they are in fact equal. We can go so far as to say they're equal, okay? Because the non-permissibles are the same. When I canceled out that negative 3 here, there was no x in that, so it's not like I canceled out a non-permissible. These are wonderful, yes. Okay, now they're not only equivalent, we can take it one step further, they're equal. Okay, I hope that makes sense.
Give an equivalent expression to the following using the stated NPVs.
Okay, here's another good question. And it's good because we're still trying to kind of tweak on this idea of equivalent. And I know we keep hitting that same idea over and over again. And again, like I said before, I hope you're getting sick of it. I hope that this is starting to become a bit of a bore, but if it's still coming across as new material, then we need to keep looking at this, okay? So I want to give an equivalent expression to this where the non-permissibles are plus 1 and minus 1. Now take a look at this. What's the non-permissible here? Well, remember, it's not 0. I could actually plug 0 in. 0 divided by 0 minus 1. Well, 0 minus 1 is negative 1. 0 divided by negative 1 is just 0. That's fine. 0 divided by negative 1 is 0. That's not a problem at all. I have no issue with that. However, if you plugged in a positive 1 here, 1 divided by 1 minus 1, well, 1 minus 1 is 0. 1 over 0 is undefined. That's no good. So this has a non-permissible at positive 1. What it doesn't have is a non-permissible at negative 1. So this is what we're going to start with here. We're going to get x over x minus 1. Now, we're going to create an equivalent expression here. Notice that the non-permissible here, and maybe I'll write this underneath here. The non-permissible is that x cannot equal positive 1 here. Now, this is going to be equivalent to x over x minus 1. Now, if I just stayed there, they're equal, okay? But I'm not going to. What I'm going to do is I'm going to introduce another factor down here that's going to have a non-permissible of negative 1. And now I hope that you've seen this enough that you know that this is going to be x plus 1 down here. If I put an x plus 1 down there in the denominator, now I've got a non-permissible at -1. Okay? Now, but I can't just do that because this is a radical change to this problem. Okay? I can't just change the denominator here. If you do something to the denominator, you have to do the exact same thing to the numerator, okay, in order for them to be equivalent. Okay? Now, not equal. Not equal, because now my non-permissibles are x can't equal 1 or -1. The non-permissibles are not the same. But that's the only place where these two functions are going to differ. Now, and hopefully what I do next here will really make sense of the equivalent versus equals, because right now I'm going to put an equal sign here. So this thing is going to be equivalent to this, but this will be equal to what I write next here. And what I'm going to do is I'm just going to distribute that numerator through, so x squared plus x. And then in the denominator here, these are binomial conjugates. Hopefully you're familiar with that. That's something you should have been looking at for the last couple of years. It ends up being like a difference of squares. This becomes x squared minus 1. Okay, the non-permissibles here, I shouldn't really have to write them, but just so that we're clear on this, will be 1 and -1. Whoops, no idea why I just put that there. 1 and -1. These two are exactly the same. These two are almost exactly the same, except for that one value at -1. Okay, so now we've taken this and created an equivalent expression with those two non-permissibles.
Find the values of A and B in the following.
All right, now this last question in this lesson here, this is kind of an interesting one. This strikes me as a sort of a question that would make it a good exam question, okay? So when the expression x squared minus bx minus 14 over x squared minus 6 minus x is simplified into the form right here, okay? X minus a over x minus 3. Now, this is our goal here. Now, we're taking this thing and simplifying it down. Now, I want to talk about that. When I start with this thing right here, x squared minus, whoops, sorry. I didn't write that out. X squared minus bx minus 14. The denominator here is x squared minus x minus 6. Now, I'm going to factor that first, okay? So, I already know, for example, that x minus 3 has to be a factor here. Okay, because when I simplify it, I don't introduce new factors, I cancel common factors. So the fact that x minus 3 survived means that x minus 3 must have been in the original there. So what do I have to multiply by -3 to turn it into -6? Well, the answer is +2. So what I'm missing here, and notice actually this is consistent with what I'm seeing just above that. The non-permissibles here are +3 and -2, and that's the same. Now, what that means here is that I canceled an x plus 2 from the numerator, because notice when I simplified it, there was no x plus 2 here. There's this x minus a and then this x minus 3. So what that means here is that this must be equal to, and I'll write this down here as x minus 3, x plus 2. This is equal. I'm not going to do anything. I know there must be an x plus 2 here. Now, I also know that one of the factors here has got to be x minus a. Okay, x minus a. Okay, good. Now, I got to think about this here, because when I multiply these two out, I'm supposed to be getting this. Now, notice that that -14, that constant at the end here, should be the product of this and this. So, -a times 2 should be equal to -14. Well, the negatives will cancel, and when I divide, I'm going to get that a is equal to 7. Okay, so this has got to be the same as x minus 7, x plus 2, over x minus 3, x plus 2. So I know right now, good, got it, a must be 7. Now the question is, what's b? Now, to get b, what I have to do here is expand this out, because notice I'm getting b here from the expansion. So I'll expand out the numerator and denominator. So this is going to be x squared, that's going to be positive 2x minus 7x. So 2 minus 7, that's going to be -5. And then minus 14. And I don't really have to expand out the denominator because I already know it's going to look like that. Okay, so notice I've got this string of equalities here. Nowhere are these things equivalent, okay, because everywhere I've got all the non-permissibles, everything is here. It's just that the pieces, I'm not quite sure what they are, and that's what I'm relying on the equality to figure out what that is. Now, compare what I've got to what the original is, x squared minus, okay, there it is. So therefore, b must equal 5. Okay, good question here. B is equal to 5, A was equal to 7.